In this video, we are presenting a method that can detect manipulation in images by utilizing Planckian locus. Consider this image and this object. The image manipulation goal is to crop and paste this object into the image. Now, if this person does some color manipulations on the object to make its color closer to the image and then paste it, the result will be this, which looks convincing to human eyes. So here we want to propose a deep learning based method that can detect manipulation in images even when it is convincing to human eyes. When an illumination beam hits an object, there are two types of reflections, specular and diffuse. Specular is the pure light coming back from the object, while diffuse is what enables us to detect object color. What a camera sees is a mixture of these two. Camera specular percipience depends on the angle of the camera, whereas diffuse is scattered all over and is not dependent to the camera angle. Color scientists like to analyze color in the chromaticity coordinates. In this representation, an observed color is a convex combination of the specular chromaticity coordinates and the diffuse chromaticity coordinates. Now let's talk about our proposed method. Consider these 2 points in chromaticity coordinates as specular and diffuse. Therefore, chromaticity coordinates of an observed color is always somewhere in between specular and diffuse chromaticity coordinates. And if we have many of these pixels, they eventually form a line. On the other hand, Planckian locus illustrates temperature of typical color of illuminations. In previous work by Baptiste Mazin et al., it was shown that intersection of this line and the Planckian locus represents the specular color. For example, natural light, which is known as white point, would be somewhere around here on the locus. If the color of the specular is not same as the white point, there are inconsistencies among specular components throughout the image. Then we suspect that the object is spliced or its color is manipulated. In our algorithm, we partition the images into various superpixels and make use of two features. First feature is color temperature of the specular for each superpixel. Second feature is the correlation coefficient of the chromaticity coordinates of the pixel within superpixel, indicating the quality of the line formed. Let's see our proposed method steps as a block diagram. First, we do on gamma correction on the image, then we transfer it from RGB space to chromaticity coordinates, which is XYZ space. On the other hand, we do superpixel formation on the image, then we compute correlation coefficient and color temperature features for each superpixel, and then form a 2D histogram based on them, which is then fed to CNN. Here, there are samples of authentic and manipulated images. The image on the left is an authentic image, while image on the right is manipulated. As you can see, histogram patterns for these two are very different. In order to make our method more robust, we took another step further and separate shadow and light areas prior to the color analysis. Now we know whether each of our superpixels are under shadow or light and apply our method to each of these areas separately and create a two-channel histogram as shown in the picture and then pass it to CNN. This is our CNN structure. The input goes through convolutional filters that each is followed by ReLU, MaxPool, and dropout layers. And at the end, we have two fully connected layers, which the last one is our classifier that tells us if an image is authentic or not. In order to test and train our model, we used some real-world pictures provided by NIST Media Forensics Challenge 2019 dataset, including 10,000 authentic and 10,000 manipulated images, which 80% were used for training and 20% were used for testing. And this result was yielded on testing our algorithm. According to area under the ROC curve, we could reach 85% of accuracy. Thank you for watching this video. I'm Setareh Kian and I would be happy to take any questions during Q&A time.